So welcome back. This is our fourth video about belief propagation, and now we are in position to state the iterative joint graph propagation algorithm. So in this case, we have a network N, and we have also a distribution P that is induced by this network. And we also need the second piece of information, pretty much like we had with the joint tree algorithm, that we had the network and also had to provide a joint tree. Now we needed to provide a joint graph. And this joint graph induces a factorization P prime. And our objective is to compute the cluster marginals and the separator marginals in a way that it will minimize the KL divergence between the true distribution and the approximated distribution. And in order to do this, we're going to exchange messages pretty much like we did with the iterative belief propagation, but now we're going to call this algorithm the iterative joint graph propagation. I'm going to say that's going to be very similar, so we're going to understand this new algorithm as a generalization of the iterative belief propagation algorithm. So the algorithm has the same ideas and the same structure that we had before when they defined the joint tree algorithm as well as the iterative belief propagation algorithm. So we start with the factors that we have in the network, and we need to associate those factors to the clusters that we have in the joint graph. We're going to do the same thing for the evidence indicators that we need to associate it to some cluster that we have in the joint graph. It's important that every factor that we have in the network must be associated to some cluster that we have in that joint graph. It's important that there will be no information loss, so there will be no factor that is not associated to any cluster. At the same time, we need to guarantee that each factor is only associated to one cluster. So there will be no overcounting of information. So we cannot take one factor and associate it to two or more clusters, because we're going to replicate the information in that factor in more than one cluster. And once we have associated the factors and evidence indicators to the clusters, we're starting exchanging messages. So now we're going to use the old notation that we had before. We're going to not use the lambdas and the pi's anymore. We can express the messages just using the this notation here, the Mij. So we're going to numerate the clusters from 1 to n, and we're going to exchange the message like from 1 to 2 and to 2 to 3 and so forth. The messages are the same that we have seen before. There is this neta here that is a normalization constant. We're gonna eliminate all the variables that are not present into the separator, and we're gonna multiply the factor that is associated to the cluster. This can be a multiplication of one or more factors, and also the evidence indicators that we associated with that cluster, and we take all the messages and multiply them together. But, and that is very important, we do not multiply the message that we received from J when we make a message from I to J, right? So this message should include everything, but it cannot include the message that came from J. All right, so now we are in position to take a look in the algorithm. Let's do that in the next slide. So here we have the algorithm. So we have this variable here. I'm going to control the iterations. We initialize our message pretty much like how we did for the iterative belief propagation algorithm. So one common and simple way is just to assign 1 to every entry, every message, and we're going to do a while the messages have not converged. And basically this is a test to see if all messages, the difference between what we have now and in the previous iteration is very small, smaller than a very small threshold, like a 0.0001, something like this. We can also add the second condition here, that is a maximum number of iterations that we can stop in the case that the algorithm does not converge. So we increment the iteration variable, and we started exchanging messages between the edges. So every edge must have two variables, must have two messages, one in each direction. See now that we are free to send the message the way that we want, because we are doing the parallel iterative version of the algorithm. So we're going to have messages that are initial messages from every node to every node in the first iteration, and we're going to multiply those messages by the factors and evidence indicators, and then we're going to have the second wave of messages and keeping doing this, right? So it's going to be very simple. The messages in the iteration T are basically a multiplication of the normalization constant, elimination of the variables not in the separator, multiplication by the factor. The message is not included, the message that I got from J, and these are all the messages from the previous iteration. And again, the same thing now from J to I, where I do not include the message that I got from I. Okay, so there is a small typo here. This should be I instead of J. And once I multiply it, all the messages, I keep iterating these until I reach a convergence. And in the case that I reach a convergence, I will return the beliefs that I have for every cluster. So I'm going to represent like this, the beta Ci, and just going to be the multiplication of all messages that I got from all neighbors. In this case here, I'm not excluding anyone, times the factor that I have in the node I, times the normalization constant, and that is the end result of this algorithm. Okay, so here we have one small example with Markov networks. Of course, this algorithm is equally applicable to Markov networks as well as the Bayesian networks. So we have the voting example that we had in the Markov network lecture with all the factors. And we have here a joint graph for this. So basically, we are just associating each factor with a cluster. So we're going to have this guy here in this cluster, have D and A. This cluster, we have C and D in this cluster here, and finally B and C in this cluster. And we look at what we have in terms of separators. Going to be A, intersection between these two guys, D, intersection between these two guys, C, intersection between BC and CD, and B, the intersection between AB and BC. Okay, for each variable, we should check if we have a tree. For A, we are here. For B, we are here. For C, we are here. And for D, we are here. So we are fine. So everything looks correct. So we can do the inference and we first associate the factors to the clusters and starting exchanging messages. So this is the association of the factors to clusters. I'm going to use this psi here to indicate the factors associated with the clusters that could have also multiplication of other factors. That is not the case, and also evidence indicators. That is not the case as well, but it could be. And now we start exchanging the messages, so we can think that, well, in this case here, let's take a look at how we're going to be step by step, like in a sequence. So this cluster 2 starts sending the message, but in order to do that, we have to predefine the message because we got no messages from C. So what we can do, that's very simple. The message from 2 to 1 will be just a sequence of ones. And we receive this message in the cluster 1. And we're going to multiply this message by what we have here. That is this internal factor that mentions A and B. So a multiplication of the message by the factor. And you're going to eliminate the variable B because this message here is only over the separator A. We keep in doing this and we have a message in both sides. So here are all the messages that we need to exchange. This is going to be a complete iteration that we have for all the messages, but now we'll probably have to do another iteration, compare to see if we have convergence or not, and keeping doing this until we have convergence or we give up and we decide to change this joint graph to something that has other properties. Okay, I know that we have discussed this before several times in different contexts, but again, we should avoid self-beliefs. So when I compute in this message here, I'm going to take the message that I got from this guy here. So they're going to be the message 2, 3. it's over the separator C. That's great. I'm going to multiply by the factor that I have here, that is this guy here. And I'm going to eliminate the variable C because this message is over D, and that is what I sent. Look that this message that I got from 4 will not get into here, right? Otherwise, I would take the information I got from 4 and send it back again to 4, reinforcing its own beliefs. So that's very important not to do this. So there are a few situations where we needed to have a valid join graph for a network that we want to build it really quickly, and the beta graph is one of these join graphs that we can use. It is a very simple join graph. It's going to be very efficient because it has small clusters and also small separators, but we can expect that it's going to be a sort of degenerate case, right? Because the separators are so small and the clusters are so small that the interactions between the variables will be lost in the inference process, so the approximation will not be good for most networks. But anyway, it's going to be a very simple way of generating join graphs for Markov networks, for instance, that we have not seen this before. So in this case, we're going to have like two classes of clusters. We have the clusters, like the large clusters. There is one cluster for each factor that we have in a network. And we have also the small clusters that is just for one for each variable that we have in a network. I'm going to have a connection between these two clusters if the variable appears in the factor. So just to be a little bit more clear, we're going to have like this factor here will be associated with this cluster. In this case, this cluster will mention the variables A, B, and C. They are the variables in the factor. I will also have the cluster for variable A, the cluster for variable B, and the cluster for variable C. And I'm going to connect this guy here with these three clusters, right? Because we have these three variables here. That's good. And we keep on doing this. So this guy here is for this factor. We'll mention variables B and C, and we can see that we have connection for B and one for C. And we keep on doing this, right? So when we need to make inference on this, we can associate each factor to each of these big clusters. The small clusters will have no factors associated because they only have variables. So we can put here a factor that is a trivial factor that only associates 1 to every entry that we have. And that's it. We can see that it's guaranteed to be 3. If we look at one variable like B, we can see that there will be a connection between B and each factor that mentions B. Actually, all factors here mention B. So there will be a connection, but this guy here only. So we're going to have a connection between this cluster 2 with all the other clusters that mention the variable B. And that's it. That's a very simple join graph. We cannot expect much in terms of approximation here for most of the networks, but they are very simple to build, so they can be useful in certain situations. All right, so it's good for this video, and let's now conclude, and we'll come back to the next one when we're going to finish with the topic of belief propagation, and we're going to take a look at the few empirical results with different techniques that are being used to use these inference algorithms in practice. So see you soon.